So what else do we know about directional derivatives and gradients? Well, suppose we have r of t, which is a curve on a surface, which is a level surface for a function f. So we have a function, we take a of it, and then we take a curve on that surface. Now, observe that if we apply this function to the curve, f of r of t should just equal a constant k. Because this is a level surface, everything on it should just have k, should just give k when we evaluate the function on it. So f of r of t should be k. And so let's take the derivative with respect to t of this. What do we get? Well, the derivative of f with respect to t is just equal to, by one of our formulas, this product, df dx times dx dt plus df dy times dy dt plus df dz times dz dt. And furthermore, we know this must be 0, because what's the derivative of k? Derivative of k is 0. If something is remaining constant, then its derivative is, with respect to t, is 0. So we know that this expression has to equal 0. So what does that mean? Well, what is this expression? This is just a dot product of the gradient of f, which is df dx, df dy, df dz, and the derivative of r with respect to t. Because the derivative of r with respect to t is dx dt, comma dy dt, comma dz dt. So if we take the dot product of those, we get this expression, which has to equal 0. So the dot product of these two has to equal 0. And what does it mean for the dot product of two things to be 0? It means that they're perpendicular to each other. So the gradient is perpendicular to every tangent vector on S because we took an arbitrary curve and its derivative, its tangent vector, is perpendicular to this gradient. So another way of saying that is that the gradient is perpendicular to the surface S. It's perpendicular to every tangent vector on S. So this is important to note. So let's look at another example. Suppose we wanted to find the tangent plane and the normal line to some surface. Let's say y equals x squared minus c squared at a point, let's say 4, 7, 3. Well, first let's note that this surface is actually a level surface of a certain function. If we move this y to this side, we get 0 is equal to x squared minus y minus z squared. So it's a level surface for the function f of x, y, z is equal to x squared minus y minus z squared. It's the level surface where we set the function equal to 0. So this is a level surface, and remember, what do we know about level surfaces? We know that the gradient of this function that we're taking a level surface of is going to be perpendicular to the level surface. So the gradient of f is perpendicular to this surface, y equals x squared minus c squared. If it's perpendicular, that means it's a normal vector. And it would be helpful if we want to find the tangent plane and a normal line to know a normal vector for this surface. So let's find the gradient, and then we'll know that that vector is a normal vector. So what's the gradient of this function? The gradient, if we just take the partial derivatives, is just 2x, comma, negative 1, comma, negative 2z. So that's the gradient. So what's the gradient at the point we're interested in, 4, 7, 3? Gradient of f at 4, 7, 3. If we just plug in 4, 7, and 3 for x, y, and z, we get 2 times 4, which is 8. We get negative 1 here. And we get negative 2 times 3, which is negative 6. So we know that this is a normal vector for the surface y equals x squared minus c squared. Therefore, we can get the tangent plane very easily. We just take this normal vector, and we take the dot product with the following vector, where the 4 comes from this 4, and we do y minus 7, because the initial y is 7, and then z minus 3. So this has to equal 0. And so this will give us an equation of for the tangent plane. So what happens when we multiply this out? get 8 times x minus 4 plus negative 1 times y minus 7 plus negative 6 times z minus 3. That whole thing has to equal 0. And if we multiply that out, 8x minus y minus 6z is equal to 32 minus 7 minus 18. So 8x minus y minus 6z is equal to 7. So this is the equation we get. So this is the equation of the tangent plane to this surface, y equals x squared minus z squared, at 4, 7, 3. Now what else did we want to find? We wanted to find the normal line. Well, we know a normal vector, so we can pretty easily from that find a normal line. The normal line, well, we know one point on it has to be this initial point, 4, 7, 3. And then we know the normal vector is this. So we just multiply that by t. And so this should give us a parametric equation that describes the normal line. We can write this slightly differently. If we multiply the t out in combined terms, we get that the line is given by 8t plus 4, 7 minus t, and 3 minus 6t. So this gives us a way to write the normal line for this surface at the point. So we can do all this using gradients and the fact that the gradient is perpendicular to a level surface.